Hello, my name is Derrick Varnes, and I will be presenting on transformer differential protection theory performed by the 387A relay by Schweitzer Engineering Laboratories, uh, and with the protections developed by myself and Danny Manzo. We are senior students, engineering students at the California State Polytechnic University of Pomona. Our supervisor on this project was Dr. Said Shan Monemi. In this presentation, I will briefly go over transformer differential protection theory. I will talk about how we implemented the protection. I will go over our project's results, some challenges that we faced, and finish out the presentation with some closing remarks from the team. Transformer differential protection theory basically boils down to that the current entering a transformer should be equivalent to the current exiting the transformer. In any other case, would indicate the presence of an internal fault. We, of course, developed the system in a CAD software known as RS-CAD and applied the protection with the SEL 387A relays by Schweitzer Engineering Laboratories. A big part of implementation of this scheme was the RTDS. The real-time digital simulator is a special purpose computer designed to study electromagnetic transient phenomena in real time. That's a mouthful. In our case, we used the RTDS to inject currents into our 387A relays to simulate breaker status signals and send trip status signals from the relays into our virtual breakers. The hardware that was used in this project includes the machine itself and a GTAO card, as well as a GTFPI card and some various electronic devices in the RTDS cabinet. The RTDS software comprises the RS-CAD family of tools, which includes RS-CAD Draft and RS-CAD Runtime. RS-CAD Draft is where the power system is built and the protection scheme is formed. A fault block component can be added to any point on the system to test for fault events. Line to ground faults and line to line faults can be specified and simulated in RS-CAD Runtime. Our power system is in a main time main configuration supporting two identical distribution feeders. Off to the right here, this is a picture of our system as it is in RS-CAD Draft with an incoming source bus at the very top here, feeding two main buses here. These transmission line models are only here to help RS-CAD separate data. Not entirely sure why this had to be done, but this is our workaround to be able to separate the mains into two main lines instead of just having one main, just to make it a little more interesting. Those mains are, of course, feeding a bus bar here that is sectionalized by a tiebreaker. This tiebreaker is normally open. This particular layout does not necessarily have an effect on our protection, but our project may be used in future senior student projects. And so we left a lot of interesting points to other students to develop their own kind of protection. At the bottom here on our feeder buses is where our transformers were placed. These transformers are identical and they're surrounded by a high side and low side breaker. These breakers are 3-pole and they can be explicitly controlled, but in our protection, we had trip signals affecting both sides simultaneously, isolating breakers for a very effective protection. And then at the bottom here, we have on the load side, we have dynamic load blocks with predefined load values that give us some very workable currents to make setting calculations a little bit more simple in the 387A relays. RS-CAD runtime allows us to simulate the system under operation and test our SEL 387A protections. This is where faults are applied and current voltage and breaker status signals can be monitored. This is a screenshot of our runtime UI. These grids here are where our currents will be monitored. These top three are phase fault currents. We just use those for troubleshooting during simulations to make sure that faults are in fact happening when we want them to. And then these bottom 8 grids here, these 4 represent the primary side currents, and then these 4 here are the CT measured currents. So they're just scaled by the CTRs for those particular CTs. And we use both of these to verify the values being shown to us on the relay itself. These LEDs here are indicating the status of all the breakers in the system. And we can use these switches to manually control these breakers if we need to. These dials are how we explicitly state if we want line-to-line faults versus line-to-ground faults versus two-phase to ground faults, and so on and so forth. The SEL 387A current differential relays typical application is transformer differential protection, which is one of the reasons why we chose to do this. The 387A was what was available to us, and we found that that was a more typical application for that particular relay. Newer differential relays, such as the SEL 487, 587, 787, provide additional functionalities. In the 387A, there's 4 different elements available for protections. You have a differential element, an overcurrent element, temperature monitoring element, and I think it's I can't think of it off the top of my head, but in this project we only focus on the differential element. Oh, and this is a picture of the rack that is holding our relays, as well as an AMS. But these 3 are the 387A relays. This middle one we are simply using as a status indicator for these for the tiebreaker. We originally had a scheme where we could affect the tiebreaker as well as the 2 transformer breakers, but we decided against it. And so we're only using the top and bottom for actual protections. This is a summary of our results from our project. The relay's 87 element trips on an internal line-to-line and line-to-ground faults and does not trip on external faults. The respective transformer breaker opens on trip signals. The status is correctly reflected in the runtime window and on the relay's programmable front panel LEDs. Excuse me. SEL SynchroWave software verifies the 87 element pickup values. A little more on that is that the relays have event monitoring, in which certain relay word bits can be used to trigger an event, in which the relay will actually record waveforms and bit values for a certain amount of time. We use this for making sure that our pickup values and certain bits were asserted correctly. This is a screenshot of the architecture for setting up a high side external line to ground fault. So these are our 2 distribution buses, the 2 transformers, of course, and then their associated breakers on the high and low sides. In this case, we are applying a line to ground fault external to the zone of protection. So we have this block connected to the bus lines here, right outside the breakers. And on this kind of fault, we would expect that the relay 87 element would not trip the breakers. These are our current measurements under a fault event. So right before here, these are the normal currents, and then the where the fault is applied is where you see these large spikes, especially on the primary side is where you expect to see the largest effect. The main indication as to why the relay worked correctly is that these CTs are still measuring current, even looks like 200 milliseconds after the fault occurred. If the relay was not operating correctly, it would have tripped those breakers, and these currents would have been wiped out very quickly. And you'll see on the next couple slides. This is the architecture for a high side internal line ground fault. So we move that fault block connection point inside the zone of protection here. It's inside the high side breaker. It's right here on the high side windings for the south transformer. And here's where we apply the fault, these large spikes, of course. And then about one cycle, maybe 1.5 cycles after that fault occurs, that current gets wiped out. The 87 element works, of course, very quickly. This is how we're indicating that the relay is working correctly, that it's tripping on that internal line to ground fault. And here's just kind of more the same. So instead of the high side external fault, it's low side. So we put the line to ground fault point outside of the zone of protection on the load side. And then we'll apply the fault. So if we look at the secondary CT current measurements here, you see where that current spikes is where the fault occurs. And the fact that that fault is still present tells us that breaker did not operate, that the 87 element did not operate, and we did not receive a trip, which is what we want. We don't want the 87 to be picking up on external faults. Now, of course, the architecture for the internal line to ground fault, we just move that fault point inside the zone of protection, and we apply that fault. You can see the spike here. And then shortly after, again, after about one cycle, it's very quick. The current gets wiped out. The CT is no longer seeing current, which is good. That means the breaker operated. That means the 87 operated and tripped those breakers when it should have on that internal fault. These are now the tests for the line-to-line faults. They follow the exact same format as the line to ground, where we move external to internal, just checking if the tripping is happening when it should be. And again, line to line, you see where the fault occurs and that the CTs are still seeing that current even after the fault, which is good. External line to line faults should not trip 87. Maybe you have a 50 element that might trip out the breakers, but since we just have 87, this is how we would expect the relay to operate. So now we test the internal faults. We apply that fault, you see that spike, and then you see the current wipe out very shortly after. That means the breaker opened, that the relay tripped on 87. That's good. So again, external load side, line-to-line fault. You see where the fault occurs, and you see that the current is still happening, which indicates correct operation. The breaker is still closed. 87 did not trip the breaker. And then we move it internal, apply that fault, and then shortly after, again, after one cycle, very fast, 87 element protection current gets wiped out. So some of the challenges that we faced in this project in the RSCAD are more like the RTDS, the signal output to the SEL 387A relay for the currents did not match what was calculated and simulated in the runtime. And the nominal values that we were expecting were not being reflected on the relays themselves. To solve this, we reconfigured the power system in RSCAD in the draft file, and we adjusted the GTAO's output scaling parameters that you can find in the RSCAD draft file. the component module for the GTAL card. The second major challenge that we faced was internal external faults or tripping. They were both tripping. We only wanted internal faults, but external faults were also doing it. So we were experiencing a little bit of a misoperation. We solved this by performing those external and internal fault trips, or external and internal faults on the high side and low side of the transformer. We would look at the operating current as well as the restraint currents that were being monitored, measured through, we used the terminal window in the accelerated quickset software provided by Schweitzer Engineering Laboratories. And we selected our differential element pickup values based off of those results. And after doing so, we ended up getting the correct operation very consistently. It 100% worked after we made those adjustments. Some closing remarks that I would like to make about the project. Our differential protection is not limited to transformers. You can, of course, extend that to several different types of power system equipment. And differential protection is really only a small part of complete system protection. The applications, of course, are limitless. Differential protection is very important when you have vital components such as transformers, especially costly replacements such as transformers. You want to do as much as you can to mitigate the damages to transformers. It can put a whole system out of operation and cost a lot of money to a power company and everyone else. And then this is just a list of our references. Thank you. I hope you learned something from this presentation. Danny and I definitely learned a lot in this project, and I think this will help in our future endeavors when it comes to any kind of protection system. Thank you again.